heat, specific latent heat. So this is the amount of heat energy needed to change 1 kilogram of that substance without a change in temperature. If we look on page 58 in our tables, we can see here the energy needed to change state. So we have latent heat versus specific latent heat. So when we're talking about specific latent heat, we're talking about being specific to its mass itself. So for the purpose of your book, they tend to use Q for heat energy. So just note that Q is the same as delta E, which is our heat energy supplied in the question. So if we go to page 166 in our books and we look at our first example here, we're going to do question 2. So here we're told that we have 500 grams of ice at 0 degrees Celsius, and we want to know how much heat energy is needed to completely melt the 500 grams. So we write down what information we're given. So we're told the mass of the ice is 500 grams. So we need to change that to kilograms. So dividing by 1,000 gives me 0.5 of a kilogram. And we know that the ice is at 0 degrees and it's melting. Therefore, it is changing state. So because it's changing state and there is no change in temperature, in other words, it's remaining at 0 degrees, then the heat energy is going to be just M times L. So therefore, if we're looking at our mass, we know it's 0.5. And L, well, what's actually happening here? Well, we have the ice is melting, so therefore it's going to be specific latent heat of fusion. As the specific latent heat of fusion of ice. So on the top of page 166, we can see that that value is 3.3 by 10 to the power of 5 joules per kilogram. So we'll multiply that by 0.5. And that gives us then the heat energy needed to completely melt it to be. So 165,000 joules. So in question 7, we're asked how much heat energy is needed. And this time it's converting 1 kilogram of ice at 0 degrees Celsius to steam at 100 degrees Celsius. So again, what information are we given? Well, we're given mass of ice is 1 kilogram, so I don't need to change my units this time. And I know that it is starting at 0 degrees, but it's ending up at steam of 100. So therefore we have two things happening. We have its changing state. So in other words, it must be melting. So once it melts, it then must go from 0 degrees Celsius to 100 degrees Celsius, and at which point then it's changing to steam. So therefore it's evaporating. So we have both a change in state and a change in temperature. And that change in temperature is from 0 to 100. So because we have a changing state, our heat energy needed must be the heat energy required to melt all of the 1 kilogram of ice. So therefore that's going to be M times L, and because it's melting, it's specific latent heat of fusion. We then have a change in temperature. So because it's a change in temperature, that's going to be MC delta theta. At this point, the ice is water, so therefore it's going to be specific heat capacity of water. Then we have a changing state again because it's changing from a liquid to a gas. So this is again going to be ml, but this time our L is going to be our specific latent heat of vaporization. So what other values do we need? Well, if we look at the top of the page 166, we can see our specific latent heat of fusion is again 3.3 by 10 to the power of 5 joules per kilogram. We need our specific heat capacity of water, which is 4,180 joules per kilogram per Kelvin. We need our specific latent heat of vaporization, which is 2.3 by 10 to the power of 6. And again, that's joules per kilogram. And then we also need our change in temperature, which is clearly just 100 degrees. Okay, so if we sub in our values, we have delta E or Q, whichever you prefer, is equal to our mass of ice, which is just 1, times our latent heat of fusion, so 3.3 by 10 to the power of 5, plus the mass, which is 1, specific heat capacity, and it's now in its liquid state, times the change in temperature, plus the mass times the specific latent heat of vaporization, so 2.3 by 10 to the power of 6. So multiplying all of that out gives us 3.05 by 10 to the power of 6 joules. And of course 10 to the power of 6 is million, so that could also be written as 3.05 megajoules. Okay, so if we look at problem 8 then in the blue box on page 166, we have 20 grams of ice at 0 degrees is added to 80 grams of water in a copper calorimeter of mass 50 grams. The temperature of the calorimeter and the water is 25 degrees, and we have to find the final temperature of the calorimeter and water, assuming that no heat is transferred to or from the surroundings and that all of the ice melts. So what we have to look at here is what is going to happen. If we add ice to warm water, well, clearly the ice is going to melt. But as the ice melts, it's taking the heat energy from the water to do that. So therefore that means that the water is actually going to lose heat. And of course the water is sitting in a copper calorimeter, meaning the copper calorimeter is also going to lose heat. So for these questions where one is gaining and losing heat, we have to look at the fact that if we have no heat transferred to the surroundings or from the surroundings, then we are assuming for calculation purposes that the heat gain by the ice must be equal to the heat loss of the copper calorimeter and the water. So if the ice is gaining heat, well, what happens to it? Well, it changes temperature and it also changes state, because if we're looking at the temperature of the water, it's at 25 degrees Celsius. So therefore the ice will begin to melt. So therefore that's going to be ml, and it's going to be specific latent heat of fusion for ice as it's melting. So I'm going to put a little I here for the ice, but it's also going to change temperature. So that's going to be mc delta theta, and that's for the ice. And of course specific heat capacity of ice is the same as water, so it's just our 4,180, and our change in temperature by the ice. The water isn't going to change state, so it's just going to be change in temperature, so mc delta theta for the water. And the copper calorimeter is also going to change temperature and not state, so therefore it's mc delta theta for the copper calorimeter. So let's write down the values that we have. So we know the mass of the ice is 20 grams, so we need to divide that by 1,000, so that's going to be 0.02 kilograms. We have the temperature change for the ice. Well, the temperature change from the ice is going to be the final temperature minus the initial temperature, which is 0. We have the specific heat, the latent heat of fusion. And again, on the top of page 166, we have 3.3 by 10 to the power of 5 joules per kilogram. We have specific heat capacity of water, so 4,180 joules per kilogram per Kelvin. And then we have the mass of the water is 80 grams. So again, dividing by 1,000 gives me 0.08 kg. And we have the mass of the calorimeter is 50 grams. So again, dividing by 1,000 gives me 0.05 kg. The change in temperature of the calorimeter and the water is going to be the same. So our delta theta there is going to be starting at 25 and it's going to cool down. So it's going to end up at theta. And then we obviously need our specific heat capacity of copper. And again, top of page 166, we have 390 joules per kilogram per Kelvin. So if we sub in all our values into our equation, we end up with 0.08. Sorry, for ice it's 0.02 times fusion, which is 3.3 by 10 to the power of 5, plus the mass of the ice, so 0.02 by 4,180. And then change in temperature of the ice is just going to be theta minus 0, which is of course just going to be theta. And then that must equal, so if I go on to the next line then, mass of the water, which is 0.08, and then times specific heat capacity for 4,180, multiplied by our change in temperature, plus for the copper calorimeter, so 0.05, times 390 times 25 minus theta. So we have to multiply out our left-hand side there to simplify, and then the right-hand side to simplify. So that gives us 6,600 plus 83.6 theta is equal to 8,360 minus 334.4 theta plus 487.5 minus 19.5 theta. So if we add all of the thetas together, so if I bring all the thetas to the left-hand side, well, that gives me 437.5 theta. And if I bring all the numbers to the right-hand side, that gives me 2,247.5, which means then that the final temperature is 5.1 degrees Celsius. Okay, so on page 166, what you're going to do for me now is question 1, question 5, question 9, and then some fun ones, which is going to be question 11, 12, and 13. So some good thinking questions there. And you'll have to remember from before Christmas that power is equal to work over time, or in other words, energy over time. And you'll also need to look at your volume. So 1 litre is 1,000 centimetres cubed.